tonight. But this is our really first start at building on a new tool. So we can still use ANOVA inside regression, and it's still looking at comparing differences of means, but it's so much more powerful in the fact that we can answer a lot of additional questions. And this is really where we get into modeling. So again, I had a couple of questions of why are we studying this and how does this really fit in? And it's kind of like a typewriter. Like we learned a whole bunch, now we're coming back, and we're going to pick up kind of shifting gears, or maybe not like a typewriter, shifting gears, and we're going to start building onto this idea of correlation. And as soon as we get a little bit farther down the road, we'll see how these means come back in. Sure, is we're going to model means. That's the big idea. We're going to say, given an explanatory variable, how can I get a better estimate of y? If I can get an explanatory variable x, how can that give me a better estimate of y? We're going to start that tonight. If you took the Stat Bridge course, you're going to see some of the data sets that we went through in the Bridge course just to underline those ideas. But right now, it's a good time. Students usually find that this is an easier section, and so you just went through that midterm. We kind of just not a time to totally relax, but it's not super intense, but it's going to build. We definitely want to have this in stone. So there's that first part. And I looked again at some of the questions. I might address some of those as we go on. If not, then go ahead and let them rip. So, but I thought I'd first start off with a little presentation. And today we're going to look at correlation. So in correlation, let me give you the big picture. I said you'll see the big picture later. Why not just give you the big picture now? So the big picture is this. We're going to have some variable, say x, and it has different levels. I can't underline this enough because this is some issues that I have continuing into 6372 that we want to just get out of the way now. X is going to be continuous. When we're talking in a regression sense, this variable on the x-axis is a continuous numerical quantitative variable, not categorical, not nominal. Like in ANOVA, we could make these different groups, group 1, group 2, group 3, handicap, wheelchair, amputee. This is, when this is a continuous variable, we can do a lot more, and that's what we're going to get at with regression. And so we can model this thing called y. This could be height, and this could be weight, or this could be time. We could have a time series, and this could be stock price. All those are quantitative. And we could see that we could take different observations along this x-axis. And as we take observations along this x-axis, if we see that x helps us explain something about y, then that's awesome, right? And it looks like it does. It looks like as x gets bigger, this is suggesting that y is getting bigger. And where we're going with this, just so we can start filling in the blanks from an early stage, I'll come back to this PowerPoint, is I want to model this. And what that means is I want to eventually build a line through there, and we'll have, starting next week and the week after that, we'll have how that line actually comes about. You remember from the Bridge course or from intro stat, whatever stat you took in your undergrad, kind of what we're doing here, but just as a review, of course, if x is big, I'm not going to guess y being small. And of course, if x is small, I'm not going to guess y being big, because that's not what the evidence is suggesting. The evidence is suggesting this trend. And so I want to bring this out again at a very early stage, is what we're going to say is, let's say we're dealing here at x1. Well, it looks like my observations near x1 are somewhere in this range. And what our assumptions that we're going to make is that here it comes, that the y's are normally distributed at x equals 1. And what we're modeling with this line is our best estimate of y at x equals 1. And so what I'm going to call that is this guy right here. That's what I'm modeling. I'm modeling the mean of a normal distribution. And I'm going to call that mean and you're going to see this in the chapter, I can call it a lot of different things. I'm going to call that mu of y given x1. Let's really get, if you want to copy that down, it's probably not a waste of time. Hopefully nothing's a waste of time, but that would be a good investment of time. This is the big picture that you're looking at here, is how can I model the mean of this normal distribution? Because even if I know my, whatever observation I'm at is at x1, even if I know they're at x1, I still don't know their y, right? I still have no idea what y is. But I have a better idea if I know it's at x equals 1, if this is the trend in the data. I'll say that it has a normal distribution, which means I don't know exactly where it is, but I know that it should be normally distributed near this mean. And this mean happens in this situation to line up on this line, so that if I'm up here, say I'm over here at x2, I'm going to estimate that y has some normal distribution, and that this guy right here is mu of y given x2. And that's, of course, my estimate of the mean at y at x given 2 is different than my mean of y at x given 1. This is the big picture where we're going in the next week or two. And actually, when we continue on, this is simple linear regression. Simple because I just have one explanatory variable. But we're going to build onto this. Where are we going to go with this? Where we can add more explanatory variables that are quantitative. We can build onto it more explanatory variables that are categorical. So we'll actually have a couple lines up here describing categorical. And then even in the next semester, we're going to take it to where my y can be categorical. There's all sorts of things. My only point here is not to pile on all these things, is we're going to take it from the very beginning, starting with correlation, and over time, build it so that we know inside and out multiple regression. That's what this is called. Multiple regressions where we're going. We're starting with one explanatory variable, simple linear regression. So here it goes. So in order to do this, in order to get to where we want to go, and that's modeling the mean of these normal distributions, we have to know that x tells us something about y. We have to know that x is linearly correlated with y. And that's where we're going to start. So we're not just measuring x being correlated with y. If I ever say that, I'm implying linear correlation. That's what we're measuring here with the statistic today. Okay. So, great. Kind of memorize that picture. You're going to see that again and again and again. That's a big idea right there. So where are we going? We want to know if x is correlated with y. And that's where we're going to pick up with how can we measure that? How can we have a statistic? So let's go ahead and get started with it. Unit 8, correlation. I guess we'll go through these quiz questions. We should have plenty of time tonight, so I won't waste time, but let's go ahead and do these quiz questions. If the sample correlation between the square root of breakdown time and voltage is negative 0.648, what is R squared for the regression of square root of breakdown time on voltage? All you do is the simplest statistic, and yet so used, and I want to underline this, there's so many seeds I want to plant tonight. R squared, so easy. If the linear correlation coefficient is negative 0.648, which we're about to study in depth, all you do is square that, and you get R squared. And squaring that is 0.419. And R squared is one of the most used, and it's useful. It's one of the most used, but one of the most misused statistics in regression or in analysis. So we're going to really kind of focus in on R squared here in the future, so you won't get away from that. But that answer there was simply you just square R to get R squared. Of course, R squared is always positive. And we'll really study what R squared means. So true, false, suppose that YX pairs, that these are the pairs, the least squares fit to these data will be much different from the least squares fit to the same data with the first pair replaced by 15-1. All this is saying is, if you remember we haven't really done the least squares fit yet, which is kind of would be nice on my plot here. Actually, now that I'm on it, let's go ahead and do it. Boom. We're going to see this one in a little bit in the future. If that's my data right there, I know that that's not a very good line. That line doesn't fit the trend. And that's because the distance, very simply and intuitively, the distance between each point and the line, we did this with ANOVA, is much bigger than the distance between each point and that line. Hopefully everybody agrees. Right? The difference, if I summed this and squared this, if I squared that distance and squared this distance between that point and squared this distance and squared that distance and added all those up, it would be more than the squared distance between the point and the orange line. And what we're saying is, when we talk about the least squares fit, we're saying we want the line with the absolute smallest sum of squared residuals. That's the least squares with the least sum of squared residuals, just like from ANOVA. And it turns out we can find through calculus, through optimization, and minimization, we can find the slope and the intercept of the line that achieves the smallest sum of squared residuals given the sample that we have. It's not the white line. It's much closer to that orange line. So that's what she means, or that's what this means by the least squares fit. And it turns out that if we replace 5, 1, let's say that's 1, well, let's say that that's 5, 10, 15, 20, 25. And let's say that this point right here, let's make a point. Let's say that that point right there is the point 5, 1. If I replace that and take it away and make that point 15, 1, which is right there, that's going to shift this whole, so we said that this orange line is the line that is the least squares line. So if that orange line is the least squares line, it's going to pull that line down, that whole line down. It's got weight. We're going to see in the future that this has what we call influence. It's an influential point. If you change one point, the correlation, the linear correlation coefficient, is very sensitive to changes in the data, and it's certainly sensitive to outliers, to points that don't follow the trend. Turns out if that point was over here, it would have even more leverage. Or if it was up here, it would have even more leverage. If it's over here, it has less influence, but it still has influence. But we'll cover that in depth. The point being here is that linear correlation is very sensitive to, and we're going to see that again and again today, very sensitive to outliers because it's based on the mean. As you saw when Dr. McGee did it by hand, it's based on the mean. The mean is sensitive to outliers, and so is this. Awesome. So key concept, boom, study hours and grades. Let's go for it. Here is here's the plot of something we probably know very well, study hours versus grades. And it looks like as study hours increase, as we might expect, the grade of these 1, 2, I think there's 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That as study hours increase, it looks for these 13 individuals that there's evidence suggests that grades increasing. It doesn't mean that it's causing it. And that's the other thing is remember correlation is not causation. It's just saying as study hours go up, it looks like with this sample or this sample from this population that the trend of grades is increasing. Doesn't mean that if I study 8 hours and then go party for 10 hours that I'm not going to still get a really low grade down here. It's just it looks like there's a correlation between study hours and grades. And what we would like to do is, we would call that a positive correlation. And then we'd see, okay, well, how about this? Something that I'm sure we've all dealt with at one time or another is hours of sleep. So as your hours of sleep increase, maybe your stress level decreases. If we measured stress level from 0 to 42. Higher the stress level, we're assuming the more stress, the lower the stress level, the least. We wouldn't be surprised if this is true. The more the sleep hours, the less the stress level. And that we would call negative correlation. So this one was positive. This one up here was positive because the bigger X, the bigger the Y. This is the bigger the X, the less the Y. That one's negative. So we would like a numerical measurement. Just like anything else, we're quantitative. We want to do things. We want to run tests. We want to get p-values, and we're going to do all that today. We're going to be experts at it. We would like to run tests, so we need a numerical measurement of this strength of this correlation, of this linear correlation. Okay, so what would that be? We're going to call that R, lowercase r. So we have X bar estimates mu, We have S is the sample standard deviation. It estimates sigma. S squared, the sample variance, estimates sigma squared. Now we have R, lowercase r, estimates this symbol, which you've seen is rho. That is the population linear correlation coefficient. That's the actual correlation, linear correlation between X and Y. So great, now that we've defined it, we can often see a relationship between two variables by looking at a scatter plot. I had a question in the quiz of when do we use the scatter plot? Always. A broader, more general question is when do we visualize the data? Always, and usually the first step. We get a new data set, we might do proc means to get some summary statistics, and we plot it. Because we can get a lot of information about different transformations we want to make, about outliers that might be out there, about general trend, just by looking at the data, by plotting it in various means. Heat maps, scatter plots, box plots, histograms, QQ plots. We can get a lot of information very quickly just by looking at the data. And I'm going to really show in the next couple of slides of why, especially when we're doing regression, we can't just look at R. We have to look at the scatter plot first. And you saw that with Anscombe's data, is you could get a very high R or a very low R when there's significant correlation or when there's actually no linear correlation at all. So scatter plot, here it is right here. So here is kind of what you'd expect. R cannot be any bigger than 1, and the closer it is to 1, it's a function of both the slope and the tightness around the line. So R, if it's a low slope, but the data is really close around the line, you'll have a very high R. If you have an extremely high slope and it's a little more scattered around, that'll still be an R, and of course, it'll still be 1. And so it is a function of both how tightly it's correlated, how tightly it is around that line, and also the steepness of that line. So you can see here's kind of what you would expect, right? This is 0.851, pretty scattered as it gets more and more tighter until it just becomes perfect correlation to 1. And that works for negative correlation as well. There we have it. That's certainly looks like there's negative trend, but there's a lot of variation along that trend. So that's about a negative 0.702, less variation, and finally perfect correlation of a negative 1. So great. So you might expect, oh yeah, that makes sense. No correlation should be R equals 0, right in the middle. And that is, if two things are truly independent, you're looking at X and Y, evidence that they're independent, low and high values of X generate low and high values of Y in the sample. So it looks like there's no correlation, looks like independence. However, beware, because notice what would happen if you did not look at the scatter plot and you just looked at R. We would totally miss correlation in the data. These data are super correlated, just not linearly correlated. So we cannot just look at R. We have to look at the scatter plot, and R, really look at the scatter plot first, and R provides us a measure of the strength of the linear correlation. And one that I need to add here that's so important, that you saw in the Anscombe's data, but if you have something like this, these are data points. We're going to get to where we can model something like that. It certainly looks like there's a relationship between X and Y. Looks like knowing something about X definitely tells me something about Y. It's just not a linear relationship. And you could fit a line to it, but if you fit a line to it, you're underestimating here, you're overestimating here, and then you're underestimating again up here. And we're going to have methods that we can use to fit this trend, but R here would probably be something like 0.82 or something like that. But a line is not an appropriate fit here. So again, we have to look at the scatter plot first. The scatter plot's more important than R. R provides a measure of the linear relationship once you know that there is a linear relationship. A line here is not appropriate. A curve is appropriate, and we're going to be able to fit that. We'll be able to find a function of X that will fit that curve, notice here that we're still making the same assumptions that what we're trying to do is model the mean of a normal distribution conditional on x. And all that means is, hey, give me everybody that has x equals 1. I'm trying to find out something about y. If x1 is here, then that's something about y. Up here, if that's x2, then we're going to say that the standard deviation of that normal distribution is the same, but we're still modeling a normal distribution is going to be our assumptions. And we're going to be able to find all kinds of things, confidence intervals, prediction intervals, just based on that. And it's a natural progression along the line. But right now, we're just measuring, is there linear correlation in the data? Is the line appropriate? So we must plot it first. Okay. And again, fire off any questions as you got them.
Yeah, I have a question.
Yes.
So if along the line the data is symmetrical, then what happens? Like, can we treat it as a linearly related or not?
If it's symmetric?
Yeah. So along the line, like the number of points that are below and that are above the line, that are same. So it's like a symmetrical shape it forms. So in that case, can we treat it as a linearly related? Because the under and the over assumption will be the same, right?
Well, let me make sure I understand what you mean. Like you could have data like this where you have repeat observations. Are you saying something like that?
Yeah.
Sure. Well, I mean, that's what we're saying here is that the difference, right? Eventually, what we're going to do. Let's do it this way. Eventually, what we're going to do is try to fit a line. And one of the beautiful things about fitting a line is its interpretability. Because as we know, lines have slopes. And if lines have slopes, what's that saying to us is that the difference in y, let's see here. That the difference in y from x1 to x2, the change in y, when x goes from 1 to 2, the change in y is that much. When x goes from 3 to 4, the change in y is the same amount. That's what we're assuming when it has a linear relationship, and that's something that we haven't been able to do in ANOVA. In ANOVA, we assume that these are groups, not numbers, and we can't do that. So when we have, it doesn't have that interpretation. But as long as, it doesn't matter if they're symmetrical or not, if they have a linear trend, then it should make sense for us to fit a line to it. I think I might have missed the question, but as long as it has linear trend, whether it's symmetric across the line or not, it's going to make sense for us to fit a line to it, and it's that least squares regression line that the math is going to fit here. We're going to find the slope and the intercept that minimize the sum of squared residuals between each point, or the sum of the squared residuals of the points to the line. And I'm almost sure maybe I got close to the question. Did I answer it, or did you want to follow up?
Yeah, in this case, like the distance between the points, like on the x-axis is the same, with respect to the line. So if we say like with respect to the line, the figure that forms is like elliptical in a form of ellipse. So in that case, can we still treat it as a
are you saying like this?
Yep.
Like that?
Yeah.
Yeah. Okay. So great question. I feel like we're going into the next section, but it's such a perfect segue that let's go ahead and talk about it. So Hari's saying, what if you have something like a football or something like that, where it certainly looks like the trend is linear, but you've got some weird looking shape like this. This is actually going to require a transformation for us because of all the things we want to do. Gosh, this is such a perfect question. And again, stuff we're gonna cover in the future. But what we want to do is more than the trend. Remember, this whole time, I'm going to zoom back in here. remember this whole time, we've asked for the mean. But remember how big I am on a point estimate is good, but it's not exactly everything we want. I want a point estimate and I also want a confidence interval. I want to know how confident I am that that point is even close to the parameter I'm trying to estimate. And what our assumption is going to be here, we're trying to estimate, among other things, we're trying to estimate this mean. But how good is the estimate? Because it's just based on that sample. How good is the estimate of that mean? Well, I'm going to have to build confidence intervals. And if I build a confidence interval, remember, a confidence interval is an estimate plus or minus a t multiplier times the standard deviation. And in order to get that, I have to have an estimate of the standard deviation, just like always, just like everything we did up until now. Before we pooled the standard deviation, we used all the data to get an estimate of the standard deviation. Nothing has changed. We want to use all this data to get an estimate of the standard deviation. But remember that just like when we pulled the standard deviation in the ANOVA, we had to make the assumption that all the groups have the same standard deviation, that the wheelchair group and the amputee group and the hearing group and the crutches group, all those groups shared the same standard deviation. Then it makes sense to do a contrast and throw everybody into the same group, or not throw everybody into the same group, but get an estimate of everybody's standard deviation and then pool that standard deviation if we make that assumption. Long story short, we need to make that assumption here too. The assumption for linear regression is that across the x-axis, the standard deviation remains constant. And this is not showing us that. This is suggesting that when x is 1, I have this little tiny normal distribution of y's. And when x is 2, or let's say x3, just let's go big, this is suggesting that I have this huge standard deviation. The mean might still be linearly related to this one. But now we've got this issue where I can really be accurate where I'm talking about y's down here, and this one is not. So it doesn't make sense to use all of this, right? I'm going to look at the sum of squared residuals, just like the same way I did before. I'm going to take the sum of squared residuals, divide by the degrees of freedom, and I'm going to get an estimate of the standard deviation and the standard error. But I can't do that here because these residuals are huge, and these residuals are small, and it looks like it's related to x. So our assumptions for linear regression are going to be that the means of these normal distributions line up on a line, but not only that, also that the standard deviations of these normal distributions are the same. And if they're not, we're going to have to do a transformation to make them the same. Or there's other methods too. All right, does that help, Hari? I think that's a great question.
Yep.
Cool. Awesome. So this is, and again, all we wanted to talk about. What's that?
Professor, sorry, kind of like a follow-up question to Harith. So are we then assuming that all the points on the x-axis are coming from the same same population, and there are no divisions in terms of the groups? Because what you drew on your board, for example, x3, isn't it possible that x3 maybe is coming from two different groups? So I guess how do we explain that variability, I guess?
So, okay, so it's a great question. I think you're saying how, so all of these, we're actually now getting into, this is awesome. This is like a sampler from Unit 8 to Unit probably 12. So yes, under the simple linear regression question, we're assuming these all come from the same population. That is the assumption here. Now, when they come from different populations, that's when I said that we might be able to add a categorical variable. And where we're going with all this is if we see that there's evidence of two different populations. Let me give you an example of that. Right? This, hang on. This might happen, just to show you where we're going. I'm not going to go too far down this road, but you might see something like this. Something like that, and then you come across another one and you see something like this. Right? With simple linear regression, you're like, this is terrible. First of all, I don't know what the heck's going on, but it looks like I have small standard deviations here. It looks like I have huge standard deviations there. It doesn't look like there's really a linear trend in the data. I mean, it looks like my regression line would go through the middle somewhere. This doesn't make a lot of sense until somebody notices, oh, these are, these are math scores in high school, and these are SAT scores on the standardized test. And we say, okay, that makes sense. As math scores go up, it looks like SAT scores go up. Okay, well, that makes sense, but what's up with the two groups? And somebody goes, oh, wait a second. Let's go ask this guy if he's male or female. And let's ask this person if he's male or female. And so it's that person if they're male or female. And it turns out all these were males, and it turns out all these were females. Sorry, guys. I had to make somebody male. So what we end up doing is we're going to end up having the ability to fit two lines. And notice if we fit two lines, one for the males and one for the females, then our simple linear regression assumptions are met. Because for these guys, their same standard deviation and it means there's the same standard normal distribution across. For these guys, for the females, it's a different relationship between the mean, but the standard deviations are the same, and we have our assumptions met. How are we going to do that? We're going to have to table that for a little bit. But remember, when we come back to this, all this is really doing is adding a categorical variable to our model. And we'll be able to fit different lines with different slopes and different intercepts.
Great. That really helped. Thank you.
Cool. Yeah, no problem. Looking forward. That's a perfect question. But I want everybody to keep in mind that that's great. That's where we're headed. But right now, we really want to get a good idea of this idea of correlation. So if you took the bridge course, I won't spend too much time on this, but go ahead and kind of scan those A, B, C, D, E, F, just to make sure everybody's on the same page. Somebody want to throw out a letter?
D.
D looks awesome, right? It's negative correlation. It's not perfect. It's not weak. Somewhere around there. That looks like a little bit stronger, but in the opposite direction.
E.
And E is the correct answer there. It looks pretty tight correlation, and it's certainly positive. You get rid of all the negatives. It's not perfect. I said it's not perfect, but it's very strong. So it's better than, it's less than 1, but more than 0.32. So awesome. So some properties that we might want to remember, this could be multiple choice questions on the final. R is, of course, between -1 and 1. R is the value does not change if all values of either variable are converted to a different scale. Scale here meaning like if feet are changed to inches, linear scale. If feet are changed to inches, if hours are changed to minutes, the relationship between X and Y won't change. In fact, if this is Y and this is X, or if this is SAT score and this is math, and let's say R here, let's get rid of that. Let's say that we have just a couple of data points, so I don't have to pound on this thing so much. If this has an R of 0.85, if I switch SAT to the x-axis and I take math to the y-axis, it'll still have a correlation of 0.85. The regression line will change, but the correlation will remain the same. And finally, R measures the strength of a linear relationship, not a quadratic. If R is 0, it doesn't mean that the data are not correlated. It just means that the data are not linearly correlated. Very, very big. That's going to come up in all sorts of units from now into the second half of this course and beyond. So what do we need? We need a random sample. The only way, it's the same as we did in the very first unit. We'd like to be able to generalize the results of our regression to a larger population. So we need a random sample. We at least need to have that some assurance that the points are independent. If they're not independent, say they're serially correlated, maybe this is time, right? If the temperature is warm today, it's probably warm tomorrow. It's not equally as likely. If it's really warm today, it's probably going to more probable that it's going to be warm tomorrow than it is to be super cold tomorrow. We're going to handle that in the second course when we do a little bit of time series and beyond. But for now, the assumption is that the points are independent of each other. Our assumption is not that x is independent of y. That's what we're trying to measure with correlation. But a pair of xy's is independent of any other pair of xy's. Visual examination of the scatter plots must confirm that the points approximate a straight line pattern. Don't even look at R until you assess that the scatter plots form some linear relationship. And I've updated my PowerPoint slides in the on-campus class. I think I need to update them here because I think when we do our examples, I have not put the scatter plot on there. But rest assured, I have looked at that scatter plot before finding R. Outliers must be removed if they are known to be errors, not just because they are outliers, but if they are known to be errors. The effects of any outlier should be considered by calculating R with and without outliers included. It's not advised to delete them if they're simply outliers, but that depends on the purpose. And we're not quite there yet, but I'll just let it out here. Regression is us building this line here. There are two main purposes of building that line, of trying to model that trend with a line. One is to interpret the slope. Maybe I want to know how math is related to SAT score. The other one is to predict. Maybe if I have an X3, I want to predict what somebody's SAT score is. And those are two very different uses of regression, and we might handle outliers differently based on where we're at there, based on which one we want to do. So, well, we'll get there. So how do we find R? This is one formula, and it's actually a pretty easy formula if you have the X and Y data. But I put it up there just to show that there's a lot of different variations of how we can find R. What was I going to say? We found in class, in the video sessions, you saw another way, which is a very easy way to do R. Most of the time in practice, you're going to use a calculator, you're going to use SAS, you're going to use some sort of online calculator, you can use Excel. All of those can give you R very, very quickly. We've got to remember that R is the linear correlation coefficient. In this case, this was on a TI-83 calculator, and it just comes up as R. And of course, there's R squared right above it. And this is the key. If we were playing a video game, this is like you opened up the magic screen. Like you did left, left, right, right, up, down, A, B, and this pops up. This is very valuable, and I want you to think real quick what it means. Should do a breakout on that and just say, hey, what does that mean? But if we know that, let me just ask. Let's throw that out there. I should throw that and do a breakout. If we know that this is true, remember that tilde means distributed. That tilde means that R times the square root of n, which is the sample size, minus 2, divided by the square root of 1 minus R squared, which is the sample linear correlation coefficient, is distributed T with n minus 2 degrees of freedom. If you know that, what can we do with that? Probably a lot of things.
The confidence interval, I would think.
Bam! That's awesome. Great. We can build confidence intervals for R. In addition to that, if we have confidence interval, there's a one-to-one correspondence between confidence intervals
and hypothesis testing.
And a hypothesis test. I'm going to focus on hypothesis test. If I know the distribution of this statistic, then given an R, I can say whether or not that is likely due to chance or if that's likely not due to chance. What I'm really saying is it likely that I'm going to reject the null hypothesis that rho is equal to 0? So this is what we're testing. Man, this is great. With that right there, HO, we're testing this. Rho equals 0 versus HA, rho not equal to 0. Remember, rho is the population linear correlation coefficient. And this is saying the data in the population, the data are not linearly correlated. Not saying they're not correlated, they're not linearly correlated. And this is saying, yes, they are to some degree linearly correlated. And so if I look at a sample of data and they're not correlated, the R is not going to be 0. R is going to be 0.1, R will be negative 0.05, R might be 0.3 if there's a small amount of data. Our question, just like always, is R far enough away from 0? Is it significantly far enough away from 0 to suggest that that did not happen by chance, which is saying it has a small p-value? Is R far enough away? Is that R of 0.999? Remember, imagine if R is 0.999, that's very unlikely to happen by chance if it really should have been 0. And that's what this will be able to tell us. Once I know the distribution, I can find p-values. If I can find p-values, I can do hypothesis testing. So, okay, we talked about R squared.
Professor, before you move on, quick question. So rho is the population parameter. What x bar is, what mu is to x bar, rho is to r?
What mu is to x bar, rho is to r. Perfect.
Okay, thank you.
What sigma is to s, and what sigma squared is to s squared. Perfect. That's right. So let's take a second and go ahead and interpret r squared. And you want to copy this down or memorize it or just make sure you get the PowerPoints and look at it again. We're not going to get away from this. And the more, we've talked about it briefly. Remember when we found r squared for the ANOVA? R squared, when we look in the ANOVA, was the sum of squares between divided by the sum of squares total. And what that equated to was the percentage of variation in the data that's explained by the model. And so far, all we had was the separate means model and the equal means model. And now we have a regression model. But there's a certain amount of variation in the beginning. There's a certain amount of variation in the data. And R squared is simply the proportion of that variation that is explained by the model that you're implementing, the model that you're doing. In this case, a linear regression model.
Professor, so the portion that's, so R squared is telling you what proportion of the variation X explains of Y or Y explains of R since they're linear. What if, but it only, you're not going to get R to be 1. There's going to be, it's going to present some percentage, let's say 64%, 0.64. So 36% of that I would think would be unexplained. And would that be unexplained by chance? Would it be unexplained because of some other variable, a covariate that we're not considering? What is the unexplained amount of the variance?
Right. So and that's the big question. You said it when you said could it be explained by another covariate? There is uncertainty and noise in the data. And so if you, just like our SAT scores, right? These are people. It's hard to explain people. But when we look at them, SAT, what is driving the increase? Something is driving the increase in those SAT scores. It certainly looks like math has something to do with it. But if you tell me the math score, I can't tell you the SAT score, of course. So actually, this is perfect. Let's talk about that right there. If I did not tell you, jump on this idea real quick. If I did not tell you the math score, you would just have a pile of SAT scores that went from here to here, right? Because that was the biggest one, and that was the lowest one. Pretend I don't have math at all. All I would do is collapse all these points over here. And if I said, hey, Nancy's up there, guess what her SAT score is? And if you had that data, right, if I pulled all these points over, you just have a bunch of points on here that went between here and here if you did not know math. And you'd have to guess, well, it's somewhere between an 800 and a 1020. Right? So the variation would be from here to here. That's the range, but that's a measure of variation. And so I'd say, oh, okay, well, that's a pretty big range. Thanks a lot. You're probably right. Her score is between there somewhere. But then I said, well, let me guess what Nancy's score is. Let me tell you that she got a B+ in math. She got an 89 in math. So, okay, well, let's say an 89 is right there. If you tell me that, given the data, now I can guess it's somewhere between here and here. Right? Because knowing something about math tells me something about the SAT score. No longer am I going to guess down here because I know I know extra information. No longer am I going to guess up here because it looks very unlikely that it's up here and down here. Let me say this, if my assumption is correct, and those SAT scores have a normal distribution at 89, which basically says, give me a whole bunch of people that scored 89 in math, let them all take the SAT score, their grade should fall in here somewhere. And it's not impossible, but it's unlikely to be this high. It's not impossible to be unlikely it's this low. So my variation went from here to there. Some of that variation was explained, and that's what R squared represents, which, as you just said, that means, let's say that this is 60%. So R squared is 0.6. So 60% of the variation is explained, right? This was reduced, and that's 40% of what this is. This is the range again, so it's not exactly the scale, but it's been reduced. There's 40% left, and that could be, right? Why did some of these people score high with an 89? Why did some of these people score low with an 89? Because people are more than math scores in high school. They eat, they sleep, they have brought up differently. People are different, and different means variation. And so there's other factors that we might add to the model that will help us explain this variation, which we'll get to this semester. But some of it we won't be able to explain. Cool. Awesome. That's the idea. We're just trying to get better predictions and good confidence intervals for those predictions. That's our goal. We want to predict and get good confidence and prediction intervals for those estimates. Okay, so that's what R squared is. Here's a quick example. This is the price per million that basketball players got paid, and this is the maximum amount of points they got in any one game that season. So it's kind of a weird statistic on this side, but this is the maximum amount of points that a player played in the season. So this guy, Dwayne Wade, he scored almost 50 points one game in a season, and sure enough, he gets paid a lot. It looks like people that get paid more is correlated with how many points they score. To underline the causation, you could pay me $14 million, and it's not going to cause me to score 1 point because I'm going to get swatted and knocked around the court all day no matter how much money you pay me. It's not going to cause anything. It's saying that given the data, there's a correlation between price that the person gets paid and the amount of points. And again, the assumption is here, just so I can keep drawing this, is that these, if you pay somebody $4 million, they don't all score the same, but they have about a normal distribution. And the assumption is at 10 million, the mean has increased, but the standard deviation has stayed about the same. That at least is the assumption. And so when you're estimating the mean of that normal distribution, and that's the function that we're going to make. Again, this is in the future. All we want to establish right now is that there is a true linear correlation between points and price, or between price and points as it is. So I don't remember if I put my lines on this or not. Darn it. So I do want to draw one more thing to continue on the point that I just made. Notice that if I don't tell you price, if I ask you to measure the points, you're going to guess somewhere. If I said, hey, here's a random player, guess how many points he scored? You're going to probably guess between 1 and 49 because that was the smallest and the biggest. Huge variation. You're like, I'm never going to get this right. It's either 1 or 49 or somewhere in between there. But if I tell you their price, you can get a better estimate, which means you have explained some of that variation. If I tell you now $4 million, you're going to probably guess, I'm just drawing lines on here, but you're probably going to guess between there and there. Not that it can't be way up here and not that it can't be way down there. It's just not very probable. And so what we've done is reduce the variation from this huge range to this smaller range, which is a huge variance to a smaller variance. And we're saying that we've explained about 82.3, leaving about 17.7% of the variation to be explained. By what? By other factors, right? their height, how much they party at night, whatever, how big their hand is, do they have LASIK eye surgery? There's all sorts of things that can drive these price predictions. But that's all we're saying here is that price is a predictor, and it looks to be, the evidence suggests it's explaining quite a bit of variation. Okay, so let's get to it. What I'd like us to do today is become great at marrying two ideas, and that is the idea of this linear correlation and testing for significance. We've done lots of hypothesis testing. We're going to now blend that with a new statistic. But it's going to follow the same 6 steps that it always has. So here is an idea. We got budget and we've got gross. This is the budget of a movie. This is how much the movie brought in at the box office, total, without considering paying for everything else. This is just how much money it brought in total. And you might expect, as budget increases, the gross should increase. And so the first thing, I need to update these. Oh, I did make the scatter plot. Perfect. I did update. So the first thing we're going to do is plot the points. And you can see it looks like potentially that there is a linear correlation in the data here. At least most of us, and I would say that there is. Now what I'd like you to do though is cover up this point now. Put your thumb over that point and just look at the points that are on the plot now. Do you think that R increased or decreased without that point that I'm covering up?
I think R increased. It would be more correlated.
With or without the point?
Without the point.
Do you think it'd be more linear correlation like this than there is like that?
Yeah, it seems to have actually no, it seems to have a flatter slope.
Yeah, it decreased.
That's what I would guess, but it's subjective. But yeah, it would look like without the point, if I was to draw a line of trend, without the point, it would do something like that. And with the point, it would do something like, maybe not quite, I kind of missed it there, but certainly a bigger slope. But what I'd like to do, just to drive home that point, is to actually come out here. Let's do it while we're here. Hang on a second. I want to go. So I put some stuff out on Canvas. And in fact, I've got to get it myself. So if you go to Canvas in Live Session 8 here, you'll see SAS code, movie, and height. So I'm going to go ahead and download that. I'm going to open it. And there is my movie data right there. So if you want to do this with me or just watch on the screen, that's fine. But this is some stuff we're doing. So this is some stuff I'm doing for 6372. So this is where we're going with all this stuff. This is principal component analysis. It's so great to see growth, and that's where we're going to head to. But right now we've got data equals movie. I'm going to plot this. I'm going to put that data in the system here. And I'm going to plot it. So I can do proc SG scatter data equals movie. You can do this stuff very fast. I'm going to say scatter. No, I'm going to say plot. I'm going to say X equals budget. Y equals gross. And we'll plot it, and we'll run. And we'll do that guy like that. Oops. What did I do wrong? Oh, X. It was not recognized. Oh, did I make the wrong call?
For SG, you have to do the
star.
Y times X, Y asterisk X.
Yep.
Hang
It should be plot X asterisk Y.
Huh. That's not the plot that I remember. Hang on a second. Now you got me. So maybe I want to do this. SG plot. Make that scatter. So you guys are right, but I'm stubborn. So there you go. And just to underline what the plot everybody else is saying.
I think your phone. Oh, there you're back.
SG scatter data equals movie. Plot. Sure. Okay. Y star X. So that should give you the same idea. Dang it. All right, fix it again. Obviously, oh, gross.
Instead of y star x, it will be variables, right?
It doesn't know what y and x are.
Yep.
Yeah, because this is gross.
Budget.
Yeah. So obviously I use the SG plot, I guess, more. But either one will give you the same plot. Awesome. So the point here being that if we were to put in this, if I do proc core, data equals movie, and I don't tell it anything else, it'll give me the correlations between budget and gross. It'll just automatically calculate those for me. And you can see them here, 0.92585, which seems pretty high. Right now it's just a guess. But if I were to take this and take out that outlier, right, that was 200,601 was the point that was way up there. So if I take that point out, look at the hit that the correlation takes all the way down to 0.53956. And what I want to show you here also is that this number below is the p-value for that test of rho H naught, rho equals 0, HA, rho not equal to 0. And here, this one is huge, and it rejects. And this one is not huge, and it fails to reject. So that one point had a lot of what we call influence. So if I come back here, just to show you that it has more influence than the rest of the points, if I just erase that point, and I just erase the bottom point, if I rerun that guy, right, it's still 0.9417. So it depends on which point you erase, right? Here I erased one of these points, it doesn't have a big effect. If I erase that point, it has a huge effect. That's just underlining it. And this guy down here is the p-value. That's the p-value of the null hypothesis that rho equals 0. Here I'm rejecting it. It's suggesting that there is linear correlation. So we got to be careful when we let one point really kind of drive what our inference is. But what I want to do next, though, is for completeness, you guys are statisticians and data scientists, which there is a subtle difference in my book. But we want to be both, for sure. That's what you're in. I'd like to take my chance to put my statistical spin on everyone. Not really a spin, but to give you that foundation. This is the idea. So where did that p-value come from? It came from the fact, where did that 0.0028 come from? It came from the fact that we know the distribution of R. Under those assumptions, we know that R times the square root of n minus 2 divided by the square root of 1 minus R squared has a t with n minus 2 degrees of freedom. So there's my null and alternative hypothesis. There's my null and alternative hypothesis. I'm going to go to that step 1. Step 2 is, you can look it up, but t n minus 2. N is the number of pairs, not the number of data, not the number of x's and y's, but the number of pairs. So that's a pair. That's a pair, 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 and that's a pair. So that's 1, 2, 3, 4, 5, 6, 7. So this is a t with 5 degrees of freedom. That's a t with 5 degrees of freedom at 0.025. Look it up, it's 2.57. Step 3, I'm going to find my test statistic. That 0.926 we got from SAS. 0.926 times the square root of n minus 2, that's 7 minus 2 times the square root of 1 minus 0.926 squared. Now I got my t-statistic. Just like that. Step 1, step 2, step 3. That is way more extreme. That's probably not happening by chance. That's way bigger than my critical value. From this t.5.48, I can get my p-value. I'm just shading to the left and to the right. My p-value is the same p-value. If you look that up, I encourage you to. That's the same one you just saw in Proc Core. Of course, I'm going to reject HO, and I'm going to write my conclusion. There is sufficient evidence at the alpha 0.05 level of significance to suggest that the data are linearly correlated. Add your p-value. So this is great. This is stuff we built from the lab before the test, bringing it in stuff we did after the test. We don't get away from it. And in fact, we're going to build on it. We're going to do these little hypothesis tests going forward for nearly everything we're doing. That's why we brought it up.
Professor, question.
Yes.
Okay, so rho equals 0, rho does not equal 0, HO and HA respectively. All right, so let's say that you have a rho that's close to 0, right? In other words, how far, and I'm just thinking in terms of a line, right? If the line were parallel to the x-axis, rho, I would assume that's rho equals 0.
Yep. That's
okay.
Right.
And so that's my null hypothesis there, rho equals 0. So my question is, how far does the slope have to go up or down before you get rho not equal to 0? Because at least in theory, as long as it's not parallel to the x-axis, you know, rho doesn't equal 0.
That's right.
It's so close. It's so close to 0. I would say practically, hey, there is no correlation. These things are independent. When I see a 45-degree slope up, or both positive or negative, or some slope to that extent, I'm saying, okay, I could see that there's some dependence here. But when I have it parallel and I move it 1 degree, you just rotate it 1 degree, either up or down. Why would I reject the null hypothesis?
So you've landed on a whole slew of things, but I think the major one that I wanted to start with is that's pretty subjective. You went from 45 degrees to 1 degree. Some people might say half a degree is significant. You're touching on the difference between practical and statistical significance. So one man's 1 degree is another man's 45 degrees. That doesn't really make any sense. One person's practical significance may not be practical to somebody else. I think a cancer scientist, if they can find anything that's related to the growth of cancer, but whether it explains 1% of variance or 10% of variance, is key to them. They're trying to find any genetic marker, any drug, anything that's related to the growth of cancer, and that is a huge success if they can explain anything, because they put enough of those together and they may be able to find a cure. Right? If you're doing the Princeton Review and you're trying to see how much the Princeton Review is going to help you, and you only find that it helps you out with 0.5 points, well, it helps increase your mean score 0.5 points, but that's not worth $1,000. So my whole point here is that if it's just a little bit of slope, it depends on what we're talking about, but we may want to detect that. The second piece of it is that it kind of touches on a couple of other quiz questions, is effect size. So it takes less sample size to detect a larger slope, something that departs from 0 quite a bit. So if it has a big slope, it'll take less sample size to get there, because you can see it right here. Look at what the t statistic, the bigger t, the more likely you are to reject. Everybody, the farther t is from 0, maybe not the bigger. The farther t is from 0, the more likely you are to reject. So what drives that? Well, the correlation drives that. So you can either have really big correlation with not so big sample size, or you could actually have a big enough sample size. T doesn't care how it gets there. You could have a huge sample size here, and if this R is like 0.21, sometimes an R of 0.21 is significant if you have a big enough sample size. If you have enough points that are still suggesting that trend, it may be due to that may be due not to random error, that you may be detecting a significant rho different than 0. To your point, let's say that this is 0.1. Let's say that's 0.1, and let's say that this is 7,000. Well, we could look at it. That's probably significant. A rho of 0.1 and a sample size of 1,000 or 10,000 or whatever I said will indicate that rho is not 0, but that rho is very small. But at 7,000, as your sample size increases, so does your power. Your power allows you to detect smaller effect sizes, which will allow you to detect a departure from 0 of such little bit as 0.1. And then to conclude, that little tiny slope of 0.1 may not be practically significant to you. You may not care about that, but that's another point altogether. We're just trying to detect, is there evidence that rho is 0, that there is no relationship between x and y, or are we suggesting there is a relationship between x and y? And it's up to us as scientists and investigators to decide if that's practically significant or not. Okay. Sorry, I went on a little rant there.
No, that was good, but you know what? I had asked a question this weekend, and it dovetails right into this. So I'm going to ask it. Dr. McGee had made a statement. Let me just find it here on the video this week. That is, hold up, let me find it here. Here we go. The question was, she said, any non-zero difference between sample means can be judged statistically significant if the sample size is large enough. And two of my classmates, helped me up somewhat, and I still didn't get to the why. And as an inquisitive person, I always want to understand the why. So this is what I came up with, and please correct me if I'm mistaken, because it seems that the concept that I'm going to share here is the same thing that applies here. So as power increases, right, as the sample size increases, the power increases. That's and as power is 1 minus beta. So and beta is the probability of a type 2 error. So as the power increases, the probability of a type 2 error decreases. Type 1 and type 2 errors are inversely related. So as the power increases, type 1 errors increase. Consequently, as sample size increases, the probability of committing a type 1 error increases. That is to say, we detect as statistically significant that which does not exist, which is what was being asserted.
We might have to tackle this. This was kind of going back to the idea of, well, I guess we covered power in this one. It's just kind of going off from what our correlation talk was. But as power increases, the probability, power has nothing to do with type 1 error. As beta increases, it doesn't mean anything as far as alpha is concerned, because alpha is conditional on the null being true, whereas power is conditional on the alternative being true. Mm-hmm. So when you're interpreting alpha, you're saying, if the null is true, what's the probability that I'm going to reject and make that error? Whereas when you're saying, if beta, if the alternative is true, what's the probability that I'm going to fail to reject? But one depends on the null, the other one depends on the alternative. So it doesn't, if sample size increases, the probability that you make a type 1 error is unaffected. It's still alpha. Now the critical value will change, but it's still alpha. So
and why would the statement any non-zero difference between sample means can be judged statistically significant if the sample is large enough? Yeah.
And this is where everybody, the big operative word these days is big data, and this is where traditional statistics, I won't say break down, but this is why other methods are needed for these huge 100,000 and million row databases, because this is your test, this is your T. This is your test statistics, right? And if T, what we're eventually going to do is say if T is way out here, I'll call it T star. If that's my test statistic, I'm going to reject. If T is far from 0, I'm going to reject. And we have to, know that. And we do know that. So as T gets bigger, that means it becomes more rare, and that means we're going to reject. Well, what makes T bigger? This is T. That's N. As my sample size gets bigger, right? As my sample size gets bigger, this thing gets smaller. Right? If I make that 1,000,000 and 1,000,000, this denominator gets super small. If the denominator gets super small, then that makes T small. And I can make this anything. I can make x bar 1 minus x bar 2. I can make this 0.00005, and I can make this 0.00004. And if I make my n big enough, it'll make T huge. So if I make this 10 and I make that 10 billion, no matter what I make this, I can always find a sample size that will detect very, very, very tiny, infinitesimally small effect sizes. And that may be practical or it may be not practical, But T, for very large sample sizes, almost will always come up to be significant. And then in big data, the question becomes, what's the confidence interval? What is that practical or is that statistically significant? And that comes up in X bars. That comes up in what you were just saying about rows. When we start talking about betas and regression coefficients, that talks about betas and regression coefficients. So that's a very big point that you've touched on, is that as sample size increases, we really have to pay attention to practical significance. We can't just look at the p-value. It goes back to finding those confidence intervals.
Thank you.
Cool. Thank you. Good question. All right. Okay, so what? So what I wanted to do is, I forgot just how much more I have here, but I'm going to go ahead and send this into a breakout. And I would like for you guys to take a calculator and see if you cannot get far into this 6-step process. And then I'll take you through it. So what you're going to do when you go into the breakout session, you're going to see this very one right here. And this is an example. So I'd love for you to go into the example, go and review this. You can always come back to this one because this one is in the breakout session. And see, and you're not going to get much time, so you're probably not going to finish it because I want to finish out here. And we're going to try to actually end on time here, believe it or not. But let's go ahead and do it. So you're going to see this one. You can always come back to do this one, and you're actually going to do this problem. So breakout, you're actually going to do this parent-child height one. If you have Excel, if you have SAS up, this parent-child height data set is on Canvas. But I give you the R, so you shouldn't even need to do that. But I'll give you the R. You're just going to do the 6-step process, find the T statistic, see if you can go to online or get a T-chart and see if you can find the critical value, find the p-value, and make a decision. Just get as far through it as you can. I'll be bouncing around. You'll have about 5 minutes, I think. Surprise! There's no way to do that. Oh, really surprised. Hey, Ari. Hey,
Harry.
sorry for all the
talk, man.
bang. Sorry for all the interruptions, for all the conversation interrupted. But let's get to. We're kind of running out of time here. I heard a lot of answers. Hopefully, everybody got to the critical value and the T statistic. Here is. You should have had something close to this.
Yep.
So your critical value was 6 degrees of freedom, so T6 was 0.975. Critical value of 2.45. This is what your homework. You'll have to do a little bit of this in your homework. The p-value is really close to 0.05, but just on the other side, so there's not sufficient evidence. You might suggest that it's kind of wavering. You might suggest you collect more data because it looks like there might be, but there's not enough evidence to conclude that right this moment. But it doesn't really make too much sense. If you're failing to reject significant linear correlations, it doesn't really make too much sense to interpret R squared, but just for practice, I did it here. And that is that. Let me see what else I had on here. I think the rest of it is, oh, shoot, we got a little bit more. Luckily, we've got a little bit of time. So this is, the last piece is, this is how we can do it in SAS. Of course, I think you might have just done it. But that's the data that you can find in SAS. With Proc Core, you've got it right there, and that's the output. Actually, we already looked at that. Remember that the p-value was 0.0028. And I think I did it for the parent data here. So for the parent-child heights, we have that null and alternative hypothesis. We already knew we had all of this stuff. Oh, looks like I just redid that. So here's the parent-child height stuff. So all you did do is Proc Core. If you wanted, I only have 2 variables here, but if you would have put down here var, later on in this course and in the next course, we'll have more than 2 variables because we'll have multiple regression. If you put var mother-daughter in between proc and run, if you put var mother-daughter, it would give you the same thing. So if you had like 10 variables here and you only wanted 2 of them, just do var and those 2 variables and you'd have it. But regardless, you can see there's the p-value, 0.0569, and you can make your own decisions now, whether or not there's significant linear correlation or not. remember, you want to plot the data first. So we could have gone back and done another breakout, but this is some examples that you can look at with respect to your homework. So here's another one on crickets chirping. We're going to cover this one. And in addition, that was it by hand. And then this one was on a marathon. And then that was, we can do that one by hand. And basically, that, I guess going back, does anybody have any questions on that part? That's basically what your homework is. It's pretty easy this week. Any questions?
Yeah, I have a quick question. Not necessarily. Oh.
I can bring it back.
All right. I can go first. Quick question on the prediction piece of it. How long does that straight line can go? Meaning, can we predict for any value of y given any value of x?
You can predict any value of y is fine to predict as long as the assumptions are met. But it's a good point, and again, we're going to cover this. Your predictions are only good between your smallest observed value of x and your largest observed value of x. You can imagine that linear trend may not continue on forever for various reasons, like the SAT score. Our SAT score line can only go up to the maximum SAT score, and then it has to flatten out. So once again, and I'll table that for a little bit, but the short answer is your inference, that line is only assumed to be good between the smallest value of observed x and the largest value of observed x. Anything outside of that is called extrapolation. And it's not that you can't extrapolate, it's that you have to be sure, that you realize you are, and that you are acknowledging the fact that you don't have any data out there and you're not sure that that linear correlation continues beyond the data that you observed it on. So great question.
Great. Thank you.
Yeah. Cool. And we'll touch on that again. Cool. Another question?
Hi, Professor, real quick. Can we go back to the formula for the t-stat?
Trying to give me...
I'm just trying to see where did we get this value, like this 0.874? What's this value?
Oh, where do you want me to go?
Yeah, I mean, if you can just tell me, like, this 0.693, what value is that, 0.693?
R.
R? Okay.
Well, in which example? The breakout one?
Yeah, in
any example.
Yeah. R times the square root of n minus 2 divided by the square root of 1 minus r squared.
Okay, cool. Thank you.
Yeah, this is R. This is R, and this is R squared.
Thank you.
Cool. And that's N, clearly. Cool. All right. Awesome. Well, that was great. The thing I really love the fact we started with something correlation, and if you have the idea of correlation, that it's linear, it measures linear correlation, you'll know better after the homework, or completely how to do a hypothesis test to see if linear correlation is significant, and remembering that we have to plot the data first, because R could be high and linear correlation is not significant. So we got to remember that we got to plot the data first, then look at the strength of that linear correlation with R, and you now have the ability to do a hypothesis test, and you know how to do that in SAS as well. We've asked a lot of great questions that's going to continue us into the future with regression. I think that today's video would be really good to go back and review a couple of times before we hit these continuing sessions, because I can't tell you that, enough how a lot of those questions are going to be the key questions next week and the week after that. So awesome. I gotta run for the 6372. I have to put together some eigenvalue stuff that you guys will hit next week or next year. But
ooh, linear algebra.
Yes, that's going to pop up quite a bit. But it'll be really interesting. I think today's lecture is one of my favorites. So awesome. So, Shravya, I hope you had a good time, or I hope we kept you excited, or...
Yeah, it was a good lecture.
Entertained.
Cool. Well, you ain't seen nothing yet, because this is what we do at the end of lecture. All right. Let's go. Shelton, you're right next to Shravya. Would you mind breaking us out?
Okay.
Please.
All right.
We put all our
One.
hands in the middle like this at the end of a great lecture. Go for it.